In this tutorial, I'll show you how to create this type of shot inside Houdini. While it won't be an exact replica, you'll learn some practical techniques. First, we'll set up our sprite system by instancing planes on points. We'll cover various methods to orient them using quaternions and animate them with a custom path follow. Then we'll focus on the spheres, exploring several fascinating topics like random distribution, loops, warp and vex manipulations. Additionally, we'll dive into the shading and rendering part, where I'll show you how to customize your shading using attributes. So without waiting any longer, let's dive in. To ensure compatibility with various render engines and gain better control over the orientation, we won't be using Houdini's default sprite node. Instead, we'll create our custom sprite system. Let's begin by setting up a geo node and naming it sprites. Enter the node, then add a grid and a UV quick shade node. Choose your preferred sprite texture. Any sprite displayed on a grid will work. Adjust the grid rows and columns to match the sprite sequence, ensuring that each picture is in a single square of the grid. Next, include a for each primitive loop and place a transform node inside. Use the following HScript code in the transform node to center all the primitives. Now, let's set up the target points. Create a point with an add node and use a point replicate to generate about 10 points. Copy the sprites onto these points. First things first, set a small p-scale attribute. And rotate the sprites on the x-axis by 90 degrees to make them clearly visible. Switch the transform order to a mode that computes the rotation at the end, ensuring the sprites are centered first and then rotated. Add a primitive wrangle before the loop and set a variant attribute corresponding to the primitive number. You can display it to verify everything is in order. Depending on the sprite texture you're using, you might need to invert the scaling to get the correct display. Then, add a point wrangle on the other side to set up the variant attribute. With 4 lines and 4 columns, the sprite animation comprises 16 frames. Use a modulo to read the sequence based on the current frame. In the copy to point node, enable the piece attribute option and utilize the variant attribute we just created. To introduce some natural randomness, set a random variable using the ptinum attribute as a seed. By default, this returns a value between 0 and 1. We want a random offset to desynchronize the sprites. Since we need a random value between 0 and 15, we map the random variable to fit this specific range and add it to the frame in the modulo operation. For a clean setup, convert both the random value and the variant attribute to integers to avoid any warnings. If you desire more control, create an integer channel named seed and add a spare parameter to use a custom value for the seed. This allows you to adjust the seed as needed. Next, add a mountain node and disable the noise alarm vector option while enabling the animate noise option. To make the sprites always face the view convincingly, create a camera in the object context. Switch to the camera view in the viewport, lock it for easy movement and find the right angle and position. Once you have the desired camera setup, go back to the sprites node. Retrieve the camera using an object merge node. Use an extract centroid in detail mode to obtain a single point location for the camera. In the Object Merge node, enable the Pack Geometry option and set the pivot location to the origin, resulting in a single point perfectly centered on the camera view. Add a Wrangle node below the Mountain node and connect the Extract centroid to its second input. We want to determine the direction between the points and the camera. Get the position of the points and the camera, store them in separate variables. And set the normal attribute by subtracting one vector from the other. If you display the normal attribute, you can see that it's working as intended. When working with orientations, it's often better to use normalized vectors to avoid any issues. Now, regardless of the camera's location, the sprites will always face it, creating a more credible effect. You can optimize the computation by enabling the pack and instance option in the copy to point node, although it may not make a significant difference in this lightweight system. Currently, the sprites always face the camera, which is good, but it can become monotonous. To add more life and dynamism to the animation, let's introduce a ping-pong rotation around the normal axis. Below the previous code, create a new quaternion attribute named rot. Houdini internally recognizes this name, so be sure to use it. A quaternion consists of an axis to rotate around, and an angle that defines the rotation amount. To rotate the sprites around their normals, we'll use degrees instead of radians. Extend the spare parameter range from -180 to 180 for a full rotation. Create an attribute verb to animate the angle value. When working with verbs, it's crucial to focus on the attribute we want to affect. In this case, we want to define the rotation angle, so add a bind export and set the attribute name to angle rot. Expose the value to access it from outside the verb. In the wrangle, replace the spare parameter with our new attribute. Now, changing the value in the verb will properly affect the rotation. To achieve a ping-pong animation, we'll use a sine function, as it returns a value that oscillates between 0 and 1. First, define the frequency using a modulo on the frame value. Currently, we'll use an absolute value. The modulo will return a value from 0 to 5 every 5 frames. Export the modulo value as an attribute to observe it in the geometry spreadsheet. For the sine function to work correctly, we map the modulo value. By default, the modulo value ranges from 0 to the frequency we define, but we want it to go from 0 to 3.14. The sine function uses pi as a period. Since the sine animation is seamless, repeating a 0 to pi animation over time will make the sine function repeat seamlessly. Now, if we multiply the sine with a custom angle and observe the result, we can see that the values go from 0 to 60, and then back to 0. For now, the orientation can only be positive, because the sine function returns a value between 0 and 1. We can center its range between positive and negative values to get a balanced orientation. Let's add some variation to the animation. Instead of using a random and fit function, I prefer using a personal asset that allows variation expressed in percentage. Let's expose this value so we can access it outside the verb, and be sure to rename them for clarity. Now, apply the same process to the angle value. Ensure that all parameters have unique names, so we can control each aspect of the animation independently. Play around with the values to achieve the desired effect. To add more control over the random function, we can include an additional value to the ptnum connected to the seed parameter. You can also add an absolute value to one of the seeds. This ensures that each seed is different, making all the random values unique. Let's clean up the nodes for better organization, and if you haven't done so already, save your scene. Next, replace the absolute p-scale value with an attribute randomize. For the playback, ensure that the modulo is computed based on the correct number of steps. Since we have 16 steps in the sprite animation and the timeline starts at 0, we need to subtract 1, resulting in 15. Disable the mountain node and random rotation for now, so we can focus on the playback animation. In certain situations, you might want to accelerate or slow down the playback, depending on the context or the sprites used. To achieve this, simply multiply the frame and random by the desired value. To simplify the process, take the code for the look at rotation and put it in a different wrangle, so we can deactivate the rotation without affecting the look at function. This will make it easier to perform tests. Delete the old p-scale wrangle, and remove the degree parameter in the look at wrangle since we are no longer using it. Currently, all the sprites mainly face to the right because of the initial grid and UV setup. To have half of the sprites facing right and half facing left, duplicate the sprites and invert their UVs on the x-axis. In a new primitive wrangle, declare a string variable to store the variant. To avoid warning messages, use the i2a function to convert the integer to a string. Change the variable to an attribute so that we can observe it directly in the geometry spreadsheet. Add invert to the end of the variant string to specify the inverted sprites. Next, delete the existing variant attribute and rename the one we just created to variant. Ensure that both the copied objects and the target points have the same piece attribute. Since we now use a string to define the inverted sprites, switch the attribute type on the target points from integer to string. Now, declare a random variable and an empty string variable. Use a condition to test the random value, as a random function returns a value between 0 and 1. If we test values above 0.5, roughly half of the points will get an inverted variant. Add a string variable to the variant attribute and observe the result in the geometry spreadsheet. You should see some points with the invert suffix, which is what we want. Merge the normal sprites with the inverted ones and connect it to the copy to point node. However, we only have 4 butterflies instead of the expected 10, which are the ones that are inverted. The issue is that we haven't changed the original variant attribute on the regular sprite, which is still an integer attribute. Convert it to a string to resolve the problem. You don't need the temp attribute below. Instead, directly name the inverted variant. Delete both the attribute delete and the attribute rename nodes. Now, the setup should work correctly, and you'll see some butterflies facing the opposite direction. Now that we've fixed the direction, we activate the random rotation and adjust its values until it looks visually appealing. To fix the issue with the playback animation, instead of modifying the UVs, use the transform node to rotate the sprites. With the random rotation and mountain nodes enabled, you can observe the results. Keep adjusting the values until you achieve the desired look. Also, remove the spare parameter in the random rotation, just like we did in the look at wrangle, since we're not using it. Before moving forward, let's clean and organize the flow to ensure a more streamlined setup. The animation method we've used so far is more suitable for particles that randomly fly in a certain area. However, if you need them to follow a path, it's not appropriate. That's why I'm going to show you another method. Create a circle and set its arc type to open arc. Increase its division count. Create a point and duplicate it with a point replicate node. Change its shape to a sphere and reduce the point count. Copy the circle onto the points. Add a point wrangle below the point replicate node and name it random spin. To define rotation axis, create a random vector named v1. To display it in the viewport, define it as an attribute instead of just a variable. To achieve a truly random 3D effect, remap the random value to include negative values. Duplicate this line to create a second vector attribute and display it in the viewport. To avoid returning the same vectors due to the same seed, add a value to one of the PT_num. Create a third vector that will be the cross product of the two others and display it in the viewport. As always, it's better to work with normalized vectors when dealing with rotation. To apply the spin over time on our circles, we'll use a quaternion again, define an angle, and remember to convert it to radians. Then, create a quaternion that will use this angle, and the cross product vector as the axis of rotation. Set the rotation using the qRotate function on the first vector. By default, the copy to point node will use the normal attribute to set the orientation. Therefore, we can define our normal according to the v1 vector. Check the result to ensure it's working as expected. The cross product process is crucial to ensure that the rotation axis remains perpendicular to the normal axis. This way, we avoid getting weird and unappealing results. To animate the rotation over time, use the modulo function instead of the user-defined angle. For example, you can make the rotation increase by 30 degrees over 30 frames. which you can then remap to extend the range to 360. Now, a complete rotation is done in 30 frames. Reduce the point count to observe the result more clearly. Next, create a new variable to store the frequency, allowing us to manually choose how many frames it takes for a complete rotation. Use this variable to replace the corresponding value in the quaternion line. If you want to add some variation, create another variable to store the user-defined variation and use a round function in a third variable. By the way, the round function is significantly more convenient than the random function in Vex, for numerous reasons that are explained in this fascinating video. By default, the round function returns a value between 0 and 1. We map it to get a value between turn time minus variation and turn time plus variation, allowing for more or less variation in the rotation time. Convert the result to an integer value and replace the turn time variable with varied turn in the quaternion line. The downside of this method is that if you set a greater variation than turn time, then you might get some negative turn time value, which is not a big deal, but it makes no sense. To prevent that, we can clamp the varied turn so it can never be less than 0. Additionally, you may set a minimum value to avoid static animation. But the best thing to do here is to simply make sure that the variation is not greater than the turn time in your parameters. Now, set a high turn time value with some variation to achieve a slow and smooth animation. Feel free to set a seed to gain more control over the randomization. Add an attribute randomize node to introduce some variation in the p-scale. And reduce the scale in the point replicate node. While observing the rotation closely, you may notice that the circles are slightly rotating around their normals. To fix this, set the upVector attribute as a cross product. This stabilizes the rotation. Organize the circle paths into a network box and rename it accordingly. Continue with a for each primitive loop in which one you can use an add node to remove the geometry except all the points. Use an add node and then a wrangle to retain only the first point of each circle. We want each point to follow its respective circle. To achieve this, add an attribute verb and name it follow paths. To retrieve the curve attributes, add a resample node and connect it to the second input of the attribute verb. Connect the input position to the output position, as we'll be changing this attribute. Add an XYZ distance node to get the closest location on the curve. And connect it to a primitive attribute node to retrieve the position. Connect the prim attribute node to the output position. If it's not working, make sure the resample node is connected before the add node to properly generate the curve attributes. Now it should work fine. To modify the position on the curve, add a vector to float node to decompose the UV vector, and then a float to vector node to assemble it back. In this case, we want to modify the first component of the vector that corresponds to the location on the curve. The value ranges from 0 to 1. By adding a constant node, we can control the movement of the point along the circle. To animate the point along the spline, use a modulo on the frame and a constant node to define the frequency. We map the values between 0 and 1 and connect it to the first input of the float to vector node. Now the point is moving along the spline over time. To increase the frequency, set it to a higher value, such as 300. Add another attribute verb after the loop, and name it noise position. We could have used a mountain node, but it's also nice to see different techniques. Add a turbulent noise to the current position. Set it to 3D and connect the offset to the frame so it will evolve over time. If the animation is too fast, simply use a divide constant. Play with the noise parameters to get the desired result. Deactivate the spin to focus on the noise animation. Copy the playback wrangle that we created previously. And duplicate the copy to point node to test the system. The p-scale may need adjustment. You can use the value from the first method. Continue adjusting the values to create a smoother and more appealing animation. Reducing the number of points can give you a better overview. For now, the sprites are not facing the camera. Let's apply the lookat method we used earlier. Add a wrangle and rename it forward direction. Instead of a random rotation around the normal vector, this time we'll make the sprites rotate following their travel direction using the up vector. To achieve this, retrieve the tangent U attribute. In the loop, merge the points and the circles and set a group for the points. After the noise, use a split node to separate the points and the circles according to the group you just created. Add an attribute transfer node after the lookat wrangle and connect the circles to its second input. In the attribute transfer node, select the tangent U attribute in the points menu. Display it in the viewport. To get a more accurate result, compute the tangent U attribute after the noise. In the forward direction wrangle, set the up attribute as a tangent U vector. Let's keep it clean. Use a normalized vector for accuracy. To improve the result, add a smooth node after the noise to avoid sharp edges. And include a resample node at the beginning of the loop to get more definition on the paths. Dive into the follow paths verb node to clean it up. Now, let's add some extra details to the animation. Currently, all the points are moving along the curves in the same direction, going from 0 to 1. To make the animation more natural, we can invert this motion for some of them. Deactivate the noise and circle spin to focus on this animation. To invert the animation, use a complement node after the fit node. This will make values that were moving from 0 to 1 now move from 1 to 0. We only want this behavior for half of the particles, so we need to filter them. Add a switch node and connect the complement. The switch node uses a Boolean test to decide which value will be used. Add a compare node and connect it to the switcher input. Add a random node and connect it to the first compare input. Use the ptenum as a seed for the random value. Now, each point will get a random value between 0 and 1, and if this value is greater than 0.5, they will move backward instead of forward along the circles. Inside the loop, the points are evaluated one by one, so the PT_num is always 0. On the block Begin node of the loop, click on the Create Meta Import Node button. This will create a node that will store loop information as detail attributes. Add a point wrangle and connect the meta node to its second input. Create a new attribute called iteration and retrieve the iteration detail attribute. This way, each point will have a different iteration value and the random values will be unique for each point. In the attribute VOP, replace the PT_num by the iteration attribute for the random function. Add a constant to the iteration and expose it outside the VOP. This way, we get more control over the randomness. In a VOP, export the result of the compare node as an integer attribute called forward. This attribute indicates whether the travel direction is inverted or not. To adjust the sprite orientation based on the forward attribute, multiply the up vector by -1 using a conditional check. Apply this multiplication before defining the up vector. Move the look-at wrangle after the forward wrangle and use the same condition to invert the normal. In the attribute VOP, swap the two inputs of the switch node to correct the logic. Go to the camera view and reactivate the noise and the spin to see the results. Also, add more butterflies to enhance the animation. As the setup becomes more complex, creating a single controller to store all the parameters in one place is a good idea. Create a null node and name it control. Open the Edit Parameter Interface window and disable the Forbid Linking Parameters option, so you can drag and drop them directly from other nodes. Add a new folder named Paths. Drag the point count from the point replicate node and rename it count. Do the same for the min and max p-scale values. A vector 4 is not convenient here, so we can instead change the type to a single float or create two floats and link them to the attribute randomize values. Add a custom integer parameter and name it seed. Set its range from 0 to 100. Finally, hide the default parameters to clean up the interface and make it more organized. We can use it to control all the seed values defined throughout the system. Keep organizing your controller to get all the values you want, such as the spin values. Specify the unit for each value, like frames, seconds, centimeters, or percent. This makes it clear and easier to work with. Don't hesitate to use separators and spacers to keep your interface organized. Expose the desired values outside the VOP so you can drive them from the control node. The benefit of exposing the VOP values is that you can keyframe them. Now, let's add a rubber toy to perform some tests. If we want our sprites to turn around some objects, we need to make some small changes. Create a verb attribute to replace the random spin wrangle and name it random horizontal spin. Choose the circle orientation you want and in the verb, set a normal if needed. Create a bind export to define the rot attribute as a quaternion. Specify the axis around which it will rotate. Since we want to express the value in degrees, it must be converted to radians. Create a random node and remap it from 0 to 360. Using the p-tenom as the seed. Now, all the circles have a random rotation. This is very useful to spread the butterflies all around at the beginning. You can also play with the point replicate size on the y-axis. Next, let's move on to the next part. Hide the rubber toy. Create a new geometry called spheres and dive inside. What we want to do here is to create a set of static large spheres on the ground and several small sets of spheres flying and spinning above. Create a circle. Set its orientation to the ZX plane. Reduce its size and increase its subdivisions to get a more round shape. Rename it. Scatter some points on this circle. And uncheck the relax iteration option to get a more random distribution. Create a sphere and copy it to the points. Let's define the p-scale for the spheres. Instead of using the attribute randomize, we'll use the personal variation asset to control the p-scale. Create an attribute verb and dive inside. Add a bind export to define the p-scale value. Use the variation by % tool and connect it to the bind export. Expose its parameters and link the seed to the p-tenom. Use an add node to control the seed from outside the verb. Make sure the variation range goes from 0 to 100. Play with the values to adjust the p-scale. The bias parameter is essential here, as it allows us to contrast the varied values. Add a point relax and deactivate the use normal attribute parameter. Adjust the point radius scale and the max iterations to get the desired result. The spheres should no longer intersect with each other. But half of their size is sitting below the ground. To fix this, add a wrangle node and add half of the p-scale to the y position of the spheres. Now, add a null node and name it out big spheres. We'll stick to this for the big spheres and move forward with the small spheres. Add a point and duplicate it with a point replicate node. Set a low point count like 5 and copy a sphere on them. This is the basic model for our small spheres effect. We want to create several variations based on this model and distribute them above the big spheres. To achieve this, add a for each number loop. By default, the iteration number is set to 10, which is perfect for our tests. Move the add and point replicate inside the loop and connect the copy to point after the loop. If we pack the result, we can see that we have 50 spheres, as the point replicate creates 5 spheres for 10 iterations. Now, let's randomize some parameters for each iteration. Add an attribute wrangle. and create an attribute to store a random seed for the point replicate. Since we are in a loop, we cannot use the ptnum, so we'll use the iteration loop. Make sure to run the wrangle on the detail level. Now we can use this attribute in the seed parameter of the point replicate. Each iteration now has a different seed. Copy the pscale verb node we used previously and paste it after the point replicate. Copy the line from the random wrangle and create a new attribute for the seed. Be sure to use a different seed by adding an absolute value to it. Use this attribute in the pscale seed. Let's change the shape of the point replicate to a sphere. To get a nicer look, we need to transfer the random seed because the point replicate doesn't keep the details attribute. Now the seed is properly read by the pscale node. All our variation sets currently have the exact same point number, which isn't very interesting. To add more variation, we can create another attribute in the random wrangle. Feed the random in a desired range, for example from 5 to 16. Use this attribute in the point replicate to define the point count. Now each set will have a random number of spheres, between 5 and 16. Again, add a value to the random seed to make it unique. Next, set an attribute for the global scale. You can simply copy the previous line and define a range for the point replicate scale. Create a variable to store a user-defined seed and add it to all the seeds in this wrangle. Add a point relax to avoid penetration between the spheres. Turn on the relax in 3D space option and play with the values to get a correct result. Now add a scatter on the circle we previously used for the big spheres. 30 points should be enough for now. Add an attribute verb and dive inside. Here, we want to randomize the position on the y-axis. To do that, we need to decompose the position vector so we can add a random value to the y component. We can feed the result to have more control over the spread. For now, the values are positive, but we can center the result to also get negative values. Simply multiply the destination mean of the fit by -1. Finally, add a third value to set a global offset. This will allow us to move all points by an absolute distance. As usual, set a user-defined value for the seed. Now, let's copy the sets we created previously onto these points. Since we are not using any variants, all the sets are copied onto each point. In our case, we want a unique variant for each point. Here we have 30 points, so we need to create 30 variants. Change the loop iteration method to by piece or point, and connect the scatter to the loop input. This will ensure that there will be as many iterations as there are points. Disconnect the block begin from the random wrangle, and take out the add node. Simply connect it to the wrangle. If we turn off the point replicate, we can see that we have 30 points at the end of the loop, which is the exact scatter number. We need to set up a variant attribute for the target points. Now, if we take a look at the geometry spreadsheet, we have 30 different variants for the target points. Copy the pscale node from the source points to the target points and adjust the values as needed. Next, add another wrangle and use the PT-num to define the variant for the target points. In the copy to point node, enable the piece attribute and use the variant attribute. Now, each target point has a unique variation set. The problem now is that we can't control the distribution of variants. We need some extra steps. Change the variant attribute to PT. And use an attribute promote node to save all the variant values in a detail array. This array will store all the variant values for further randomization. In a wrangle, create a variable to retrieve the array that we just created using the attribute promote node. Then declare a new array attribute. For now, it's still empty, but the main problem is that it's stored on the points. Change the runover mode to detail to save it on the detail instead. Retrieve the length of the array in a variable. Set up a loop that will iterate over each element of the array. Within the loop, add the following lines of code. The first line allows us to get a random index in the array. The second line will add the chosen value to our new array. The third line will remove the chosen index from the original array so it can't be picked again. Now, if you inspect the new array attribute, we can see that it's the same as the original, but its order has been randomized. In a wrangle, create a variable to retrieve the array. The benefits of using this method is that now we can set a custom seed to randomize the distribution. To make the spheres spin, we use the wrangle we created for the sprites. However, break the channels as they are still linked to a controller that does not exist in this context. Instead, use your own custom values for spinning. Merge the small and big spheres together and increase their definition as desired. Next, add a point relax node to repulse the small spheres from the big ones. Set up two groups to define which points to relax and which points to act as influence points. Use the groups accordingly in the point relax node. Let's clean up everything and reorganize the tree. Don't forget to use a split after the relax to only retrieve the relaxed points and not the influence points. Create a third geometry node for the ground and dive inside. Add a grid and an unnamed outground. Copy the grid and go back to the sprites. For this tutorial, we will continue with the first animated method, but you can use the method you like. As you can see, some of our butterflies are located below the ground. Reduce their scale to make it more coherent compared to the spheres and slightly raise the initial point. Now most of the animated sprites are above the ground, but some of them are still below. Add an object merge node to import the ground we made previously. Use an extrude volume node to generate a shell on it. Then, use a group to select all the points that are inside the extruded volume. Use a ray node to confirm the selected points on the ground. Set the entity to points and a method to minimum distance. Also, use the group we just created to only affect the points below the ground. Connect the output of the ray node to the copy to point node. Now, all the points are above the ground, but some may still intersect with the spheres. To fix this, copy the big spheres node and import it like we did with the ground. Convert it to a VDB. And reduce the voxel size for better definition. Add a VDB reshape node to dilate the volume. Again, use a group to select the points inside the sphere but switch the bounding type to volume. Change the group name and repeat the operation with another ray node. This time, use the inside spheres group and not the inside group. Finally, remove the VDB reshape node since it's causing issues with our selection. Now the points should be properly placed above the ground and not intersecting with the spheres. To prevent some points from not being selected because they are very close to the ground, we can add a margin by duplicating the extrude volume node and setting a low positive depth value. Merge the two extrudes and convert them to VDB. Connect the VDB to the second input of the first group node and change the bounding type to volume. Set the ray lift to 0 and add an attribute VOP after the ray node. Connect the inside group to the first input of the attribute VOP and the ground geometry to its second input inside the attribute VOP. Add an XYZ distance node and connect it to a primitive attribute node. Connect both of their file inputs to the second VOP input. Set the primitive attribute node to retrieve the closest normal. Then, add a displace along normal node. Connect the position to the position and its output displacement to the output position. Now increase the displacement value to raise the point slightly above the ground. Let's keep it organized and clean. In the second conform, set a low lift value to repulse the points a bit more if they are intersecting with the spheres. With these changes, the points should be properly placed above the ground and not intersecting with the spheres. Let's move forward with the lighting and shading. In the object context, add a rope network and dive inside. Create a redshift node for rendering. You can of course use any render engine you like. In the object context, add also a material network and create a redshift light dome. Enable the viewport IPR. And pick an HDRI texture for the light. Adjust the rotation of the lights to ensure the shadows fall in the desired direction. In the material network, create a redshift material builder and rename it ground. Copy this node. In the object context, hide the spheres and the sprites and jump inside the ground geometry node. Don't mind the normal node here, it's not necessary for this tutorial. Add a material node and pass the material path in the material slot. Don't make the same mistake than me here, do it in the right slot. If you can't see any changes when adjusting the material parameters, maybe the display flag is set before the material. To ensure the correct evaluation, add an output node after the material network. This will force the display flag on it. For the ground, you can use any texture you like. Here I'm using a clay texture. Add a redshift texture node and connect it to the base color. Add a UV quickshade node on the ground to generate mapping informations, so the texture can be displayed properly. Adjust the texture scale as needed. Additionally, you can import the occlusion path and multiply it with the diffuse in a redshift color composite node to add more details. Use a redshift color correct node to increase the diffuse contrast. When dealing with black and white textures that are not directly used for their color, it's sometimes better to import them using a raw color space. For the ground's reflection, you can use the displacement texture to control it. Let's also connect it to a redshift displacement node and set the mode to height field. Enable tessellation and displacement in the redshift tab of the ground geometry. If you don't see this tab, just click on the Object Bounds button in the redshift menu. Increase the minimal edge length and decrease the maximum subdivision to keep it light. Adjust the displacement scale in the redshift material node. To create the sprite shader, use another redshift material builder. Connect the sprite texture to the base color of the material. Now, hide the ground and display the sprites. Add the material to the sprites. For transparency, use a redshift color splitter node to separate the alpha channel and connect it to the opacity. To improve the appearance of the butterflies, you can make them emit their own light. Connect the texture to the emission color and increase the emission weight. This will help create the illusion of light reflecting on the butterfly planes, giving them a brighter appearance. To add some variation between the butterflies, go back to the sprite's geometry object. Add a wrangle before the copy to points node and define a new attribute, for example, sat, to control the saturation variation. Set a random value for this attribute using the rand function. In the material network, import the sat attribute using a redshift point attribute node. Connect the scalar value to the saturation input of the redshift color correct node. You can remap the range as desired to adjust the variation in saturation. Ensure that the sprites are not packed, otherwise the variation won't work. Adjust the value of the sat attribute as needed to get the desired effect. To work with the spheres, add an output node after the big spheres to focus on them for now. Create a material node and create a new shader for the spheres. Use the desired texture for the shader. To display the texture properly on the spheres, add a UV project node and play with the projection type to get the desired look. To add more organic and interesting variation, randomize the orientation of the spheres. You can also use the texture to create self-illumination on the spheres. Use the diffuse texture as displacement. Enable tessellation and displacement in the Redshift tab of the sphere geometry settings. Reduce the displacement scale to a suitable value. Adjust the reflection weight and roughness to achieve the desired appearance. Create another material builder for the metal spheres. Replace the Redshift standard material with a Redshift material. You can use one of the presets, such as the copper preset. Apply it to the spheres and adjust the roughness and anisotropy. You might need to reload the viewport IPR to see the results. Adjust the camera angle to get a nice reflection. To apply multiple shaders on the spheres, deactivate the material node and use a wrangle instead. Create a string array to store all the shader paths you want to use. Use a random function to select one of the shaders from the array, and remap it to choose from any shaders in the array. Use the len method to ensure that the random selection will adjust itself based on the number of shaders in the array. Define the shop material path attribute, which is the default attribute in Houdini to get a material. In the geometry spreadsheet, you can see that each point now has either the metal shader or the abstract shader. After the copy to points node, promote the shop material path to the primitive level. Add a seed to randomize the material distribution. This way, each sphere will get assigned one of the shaders randomly from the array. It's looking great so far. To add another shader to the array and have it distributed, you can simply duplicate the shader path in the array. Now let's apply the same shader distribution logic to the small spheres. Copy the wrangle that randomizes the shaders for the big spheres and move the output node to focus on the small spheres. Rename the last material to gold and choose a gold preset. In the wrangle for the small spheres, replace the abstract shader with the gold shader. Set the output to both the big and the small spheres. Let's adjust this shader, maybe with some self-illumination. For the camera resolution, I'm gonna stick to square proportions, but you can do as you want. For the big spheres, you can add an attribute randomize node to get a random hue attribute. Use this attribute to control the hue of the abstract shader. Since the hue ranges from 0 to 360, adjust the attribute randomize accordingly. In the gold material, which is not actually a gold shader anymore, use an absolute value to define the emission color. Add a color correct node to further randomize the emission values. Duplicate the attribute randomize node from the small spheres and load the hue attribute in the redshift material of the gold shader. Ensure that the variants are not packed, as it won't work if they are. Now, display all the objects and proceed to animate the camera. Launch a flipbook to evaluate the animation. We don't want the easy in and out interpolation, so just set the keyframes to linear. We can add some turbulence to our camera. Adjust the noise values to get something you like. In the Redshift camera options, enable the legacy depth of field technique and bokeh to control the depth of field directly from the sampling menu. Play with the lens effects, such as bloom, to enhance the render. In the ROP network, select the Redshift node and dive into the AOV Manager menu. Add the ambient occlusion path, which won't be visible in the render view by default. You'll need to set it up in the shaders to make it visible in the final render. In the material, add a Redshift ambient occlusion node and a Redshift store color to a OV node. Connect the material in its beauty input and the occlusion to the OV input. Now if we launch a render, the occlusion appears for this shader only. We can add it to any shader we want, so let's do it also for the ground, the metal shader and the gold shaders. Don't do it for the sprites though. Now if we launch the render again, the occlusion appears on the other objects. Using Cryptomatte and emission passes will certainly add more flexibility in post-production and compositing. Splitting the render into two separate warp nodes for the butterflies, and the rest is a smart approach to manage the occlusion. Duplicate the Redshift warp node and call it matte. Remove the render passes. Use it to render the sprites and make sure to enable the matte option in the Redshift tab of the spheres and the ground. It's also important to enable the camera space render option in your Redshift's rope, otherwise the camera turbulence animation will be ignored. Creating a control node for the spheres, similar to what we did for the sprites, will indeed make it easier to adjust and vary the look of the scene. I hope you enjoyed this tutorial. You can find the Houdini file and the After Effects compositing file on my Gumroad page. If you have any questions, don't hesitate to ask in the comments and I'll do my best to respond. Goodbye.